Hello everyone. So the next type of problem in frame is, again we are still dealing with the non-sway frame. Again, by seeing the frame you can analyze whether it is a sway or non-sway. So in the given question it is that analyze the frame by slope deflection method and draw bending moment diagram. Okay, so this is the frame ABCD. Okay, and there is a load only on BC, and BD is overhanging like this. Okay, A and C are fixed end. Again, there is no load acting here. Okay, so even if there is any force trying to push to the right side, there is a restriction here. The restriction is this fixed support, so it will not allow the frame to sway. So just by seeing the frame you can analyze whether it is a sway or non-sway. So right now there is no movement happening here, so it is a non-sway frame. Okay, so it looks like this. It's a column beam which is fixed, and this is a overhang. Okay, all the distances are giving here, and AB, BC. Okay, BC I think it's not given, so BC is 4. This length is 4 meter. All right. So again, as usual, the steps will be same. First, finding the fixed end moments, then slope deflection equation, followed by more joint equilibrium equations, and then the final moments. Okay, so let us start with the fixed end moments. So AB, BC, and BD. So AB, start point. Okay, this is the first point, start point. Okay, so MFAB is equal to minus. See here, there is no load here. Okay, so no load, no moments. Similarly in BA, in this column there are no loads acting, so MAB is equal to MBA, which is equal to 0. MFAB is equal to MFBA is equal to 0. Then BC, it has a UDL, so MFBC is equal to minus WL square by 12. MFCB is equal to plus WL square by 12. Okay, so it's 16 kilonewton minus 16 plus 16. Next, MFBD. Okay, now see here, MFBD. So here, this is from right to left. So from right to left means plus, left to right means minus, right to left means plus. That's why it's plus 20 into 1, this distance. Force into perpendicular distance, 20 into 1. So 20 kilonewton meter. Okay, next is slope deflection equation. In slope deflection equation, calculate ST, slope deflection equation. So MFAB is equal to same formula, MFAB plus 2EI by L 2 times theta A plus theta B minus 3 delta by L. Now again you can see here, theta B will exist here. Theta C is fixed 0, theta A is fixed 0, theta D will not exist because the moment at D is 0. So only you are left with theta B value. Okay. So MFAB plus 2EI by L. So 2 times theta A plus theta B. So theta is 0. This also no settlement, 0. Then substitute the value. So you're left with 0.67 EI theta B. So it's equation number 1. Then MFBA is equal to MBA is equal to MFBA. Again same thing, 2 EI by L. Then theta A plus 2 times theta B minus 3 delta by L. So this is now 1.33 EI theta B. Equation number 2. Next, MBC is equal to MFBC plus 2EI. Okay, now I here is, be careful, I here is 2I. So substitute the value here. So that is 2I, then 2 times theta B plus theta C minus 3 delta by L. Again, theta C fixed support 0. This also be 0. So MBC, you have got the value. Again, keep it in the theta B and a constant value. Similarly, MCB is equal to MFCB plus 2EI by L theta B plus 2 times theta C minus 3 delta by L equal to, so substitute all the values and then write this equation. Okay, so MBC. Okay, then you have to write MBD. So MBD, no need to write here because MBD is nothing but MBD. Okay, it's you'll again get the direct value here. MBD I've already calculated, that is minus plus 20. So you can use it directly here. Okay, so equilibrium equations. Equilibrium equations are joint equilibrium equations. So here at one joint there are three members connecting, so we have to consider that. See here, MBA, BC, BD. Okay, consider all the equations. MBA, BC, BD. Okay, equal to 0. Substitute all the values here. Then you'll get only one unknown is there. So it is EI theta B, which is minus 1.2. Then find the final moments. So the final moments are MAB. Substitute the values here. MAB is 0 minus 0.8, whereas MFBA, okay, at B there are three members connecting. You can see here at B there are three members. Okay, so whenever there are three members connecting as such, the moments and all will not be same. So they'll be equal, they'll not be equal, they'll be different. All right, so here now M AB is equal to, we have already, MBA is minus 1.66. Just substitute the values. MBC is again minus 18.4. MCB is 14.8. See here, all three are different. Okay, and MBD is, we have already calculated, 20 kilonewton meter. Okay, only when this happens, only when there are three members connecting at a joint. Had it been just two members, then it would be equal and opposite, what we have seen previously. But because here there are three members connecting at a joint, then obviously the moments will be different. Okay. Okay, then span BC, there is a UDL. So it is WL square by 8. So W into L square divided by 8. So it's 24 kilonewton meter. Okay, so then first thing is, let us mark this. So first, MAB is minus. Okay, minus means show it like this, anti-clockwise. So it is anti-clockwise at A. Next, MBA is minus again. MBA is minus. So show it here, anti-clockwise. Next, MBC. MBC is minus 18. BC, again you have to show wherever and whichever span it is acting, you have to show it in that span. Okay, so MBC, you have to show it in horizontal section now. Horizontal section of this, so it is 18.4. 18.4. Then MBC is here. Okay, and next MCB. MCB. MCB is plus 18.4. So plus means clockwise like this. Next, MCD and then MBD. MBD is plus again. Plus means again like this. You have to show clockwise. You have shown here in red mark. So all these three moments should be near the joint B only. Okay. Don't refer this diagram. Refer this diagram. Okay. Once again. This is the correct diagram. Okay. Now see here. When you're drawing the bending moment diagram, you have to consider this. So what this moment is doing, just trying to push the this part of the column outside. So this is the zero line of the column. So this goes outside, means like this. So this is out. So it is minus. And one more thing, I've told you these dotted line here. You can see a dotted line. All I've drawn below. So this is below the beam. This is all inside the beam. If the beam bends in this inside portion, that is, if the beam or the column bend towards the dotted portion, then that would be a positive bending moment. So right now, what's happening here? It is trying to push the beam out, means away from this dotted line. So away from the dotted line, outside, that is minus. Okay. Then now to keep this in equilibrium, this column has to bend inward. Okay. So what this column will do is take the magnitude 1.66. So it should bend inward. So show it here, plus. Plus of the column from B. Okay, this much is over. Then join both of these like this. Next, come to this portion. Okay, first BD. Okay, in BD, at D it is 0, but at B it is 20. So from 0 to 20, exactly above B, it should be plus 20, like this, 20 above. Then again, same thing, at B, there is another load. That is another moment, that is 18.4. So what do we have to do? Show here plus 20 here. Then same point at B, it is 18.4. So just drop this line down here and connect both of these. And finally at C, it is 14.8. Okay, so 14.8 means again it is above this line, not inside the dotted line, so above. So just show here 14.8. Then finally connect this 18.4 and 14.8. Okay, so whatever is above this line would be the positive bending moment. Below this line would be negative bending moment. That's how we should show this. Same thing here also. Here also it is bending out, so all minus. It is bending inward plus. Then again, it's a overhang, so always start with D. Start here 20. This is less 18.4. Then join this at 14.8 and then connect this. This is minus minus above this line. Whatever you have I've shown here in the form of dotted this. I've hatched this area, so that is positive bending moment. Okay, this is how you find all the moments and draw the bending moment diagram. Okay, on the same lines, there is one more. Again, this is also a simple problem. Okay, I've just done it directly here. I've shown all the points. You can see here, it's A is the fixed support, which is connected at B here. And similarly in BC, it is at C, there is a roller support, and D, there is a fixed support, right? So it is connected like this. Again, by seeing the problem, you'll get to know how many unknowns are there. Now see here, A is fixed, so theta is 0. D is also fixed, D is 0. B is a jointed member, so connected member, so there exists theta B. Similarly, theta C also has a roller support, so that also exists. So there are two unknowns here, theta B and theta C. Okay, so as usual, again in this problem, so again by seeing the problem, you'll get to know whether it's a sway or non-sway. There are no forces acting to the right, no horizontal forces here. So even though if it acts, this this frame will not bend, because that it is restricted here and here at A and C. So it's a non-sway frame. Again, you have to write there, it's a non-sway frame. And then as usual, you have to go on finding MFAB, BA, BD, DB, BC, CB. Okay, I found out here, see. At BD, there is no load, right? So it is all 0. So go on finding this. It's a simple point load. Point load, and there is a UDL. So go on finding all the forces here. Find the fixed end moments. Okay, then bending moment. So once you find the fixed end moments, find the slope deflection equation. So slope deflection equation, that is M AB, BA, BC, CB, BD, DB. Okay, same like before, everything same like before. And see here, I value is not given. That means it is understood that I is common throughout. Okay, so this is common throughout. Then joint equilibrium equation, MBA plus MBC, BD, MBC is equal to 0. Once again, MBA plus MBD plus MBC is equal to 0. That is first one. Similarly, next at C, MCB is equal to 0. So these are the joint equilibrium equations. Once you solve them, you will get this EI theta B, and EI theta B is 0. EI theta C is minus 40. Now again, substitute here in these equations here. Okay, in these equations, so you'll get MAB, MBA, MBC. Okay, so I'll just show it here. It is a simple diagram. Most of it is 0. So MAB is minus 60. So at A, and see here again, I've shown the dotted line here. Dotted line below the beam. Then inside the beam here, inside the column, left side of the column, here right side of the column. Like this, if it is inside, like this, inside of the beam and column, the meaning of the dotted line is if the beam bends towards the dotted line, then that portion is considered as positive. If it goes opposite, that is considered as negative. Okay, so here it is 60. Okay, so this is first is minus 60, so it is anti-clockwise direction. Show it like this. Next, B, A and BC. BA, it is plus 60, so clockwise. BC, it is minus 60, anti-clockwise. Then all three others are 0. So it's 0, 0, 0. MDB, MBD, all are zeros. Okay, now next is drawing the bending moment diagram. We have already got this. Okay, so bending moment in AB. AB is a point load. So WL by 4, that is 60. Next, here there is a UDL. So it is WL square by 8. Here also happens to be 60. So now when you draw this line, just draw a single line diagram. Then here it is 60. So show 60 here, right? Next, at this portion again it is also 60. So show 60 here. Then at C it is 0 because at this point there is a roller support. So moment at the roller support or simply support is 0. So join this. Then mark all of these here. In this case it happens to be straight. All the values are 60. So just shade this value. So whatever is inside, these all negative. Whatever falls outside this line becomes positive bending moment. Okay. All right. This is how you calculate. Try this problem. So this is how you calculate the fixed end moments and draw the bending moment and the deflected shape of the beam. Okay. That's all for today. Thank you.